We studied redox reactions in Chem 1A. Redox reactions are where electrons are transferred from one substance to another in a chemical reaction. And we learned a mnemonic to help us remember which is which, oil rig, and that stands for oxidation is loss of electrons. Reduction is gain of electrons. Oops. No. So, there we've got the rig, and there's the oil. So that's one way to remember. We can also think in terms of oxidation states, another topic from Chem 1A. Oxidation states often correspond to the charge on a charged species. So calcium 2+ ion has an oxidation state of 2+. If we see an increase in oxidation state, that is oxidation. Reduction is a decrease in the oxidation state. Or you could say reduction is a reduction in the oxidation state. Okay? So the oxidation state goes down. Here we can see that calcium has an oxidation state of 0 here because elements always are 0. And in the process of this reaction, calcium gets a +2 oxidation state. The oxidation state went from 0 to +2. That's an increase. That's oxidation. In water, we've got oxygen with a -2 oxidation state, hydrogen with a +1 oxidation state. And in the course of this reaction, we form hydrogen, the element, with an oxidation state of 0. There's also some hydrogen here that doesn't get reduced and still has a +1. But some of these hydrogens are reduced. They go from a +1 to a 0. The oxidation state goes down, it decreases, it's reduced. Okay, any questions? So in a chemical equation, we must have mass and charge balance. Many times we can just balance a chemical reaction by inspection and everything's going to be fine. If an oxidation-reduction reaction is involved, sometimes that works, but many times it doesn't. Because balancing by inspection makes it very hard to get the charges correct. So we do the half reaction method. So we're going to break that redox reaction into 2 half reactions. We'll balance each of them individually and then add them back together. And this seems like an awful lot of work, but it actually is the simplest way to balance complicated redox reactions. So a review of oxidation states. Remember, oxidation states are not ionic charges. They can be easily confused with ionic charges because oftentimes the oxidation state and the ionic charge are the same number. But oxidation states are made up, and ionic charges are real measurable charges. So free elements have an oxidation state of 0. So any of the elements, when we write the symbol for an element, do we put a charge on it? No, only if it's an ion, right? But the element itself has a charge of 0. It also has an oxidation state of 0. A monatomic ion, that's a single atom like sodium or chlorine as an ion, the oxidation state is equal to their charge. So in NaCl, we know that sodium has a +1 charge. It also has a +1 oxidation state. Chlorine has a -1 charge, a -1 oxidation state. So far these are just matching together. The sum of the oxidation states of the atoms in a compound is 0. And this is the same as with ionic charges. You make a ionic compound formula, and the charges of the ions have to add up to 0. The oxidation states will also add up to 0. If we're looking at a neutral molecule, like sugar or water, H2O, the oxidation states also add up to 0. There's no charge on that. The oxidation states add up to 0. If we're looking at a polyatomic ion, then the oxidation state will equal the charge on the ion. Bless you. So here we have the nitrate ion. So this overall has a charge of -1. The oxidation states of the nitrogen and the 3 oxygens in this are going to add up to -1. The nitrogen and oxygen do not have ionic charges in nitrate, but they do have oxidation states, which you can think of as, imaginary ionic charges. And so here, oxygen's going to have an oxidation state of -2. There are 3 of those, so 3 times -2. And then there's 1 nitrogen. The nitrogen's going to be +5. And when we add these together, they're going to equal the overall charge on the thing. So you can kind of lump all 3 of those in number 3 together. The sum of the oxidation states in a thing will equal the charge on the thing. If it's an ion, it equals the ionic charge. If it's a neutral molecule, it equals 0. Metals always have positive oxidation states, just like their charges. So group 1 metals always have an oxidation state of 1 because they always have a charge of 1. Okay, so when a metal has a charge, when it is an ion, its oxidation state is equal to its ionic charge. So group 1 plus 1, group 2 plus 2. Where it gets a little bit sketchy is with the nonmetals. So in compounds, nonmetals have oxidation states even though they don't have ionic charges. And so we have a system for assigning these things where we learn this pattern, and then we can assign oxidation states, and we don't have to take into consideration electronegativities or sizes or anything else. So this is what we need to remember. You're like, yeesh, how do I remember that? Well, this column is just an example. So it's just the nonmetal and the state. So how do we remember this? Fa 765. You guys know what Fa is, right? Really good noodles. Okay, so Fa, let's just change that P into an F. Right? Fa 765. Okay, so that's this list. Fa, FHO 765. We remember that. There's actually a restaurant, Fa 76. They just need to add a 5 on the end, and I think I'll buy stock. Okay, so what's going on here? So this is the order of priority, basically. So what we're going to do is we're going to look at the nonmetal, and it has a preferred oxidation state. This is all personifying atoms and stuff, but it works for me. So if fluorine was an ion, what charge would it have? -1. So fluorine, -1 oxidation state. The list here tells us the order in which these elements get to choose their oxidation states in a compound, because they don't always get the preferred oxidation state. Fluorine will choose -1. Hydrogen ions are +1. Oxygen ions are -2. Group 7, other than the fluorine, because fluorine got picked first, but all the other group 7A nonmetals would normally have a charge of -1 as an ion. So if they are allowed to choose, they will choose a -1 oxidation state. Group 6 is -2, group 5 is -3. Okay? So you already know this stuff from Chem 1A, right? And so all we have to do is remember the order, Fa765. So let's do some examples of that. Well, maybe not. Let's make up some examples. Or we can use some of these. So if we look at something like ammonia, this is not an ionic compound, there's no ionic charges. But there are oxidation states. It's nonmetals, and so we think Fa765. Is there fluorine? Nope. Is there hydrogen? Yes, hydrogen gets to pick. What does hydrogen pick? +1. So hydrogen is choosing +1, and there's 3 of them. All the hydrogens are the same. They're all going to choose the same oxidation state. There's only one element left. And so nitrogen has to be whatever is necessary so that the oxidation states add up to the overall charge here. The overall charge is 0. And so for these oxidation states to add up to 0, the nitrogen has to be +3. This is the same way we determine charges on transition metals in ionic compounds. You look at the charge of the anion, and then you can figure out what the charge on the cation is. +3. Oh, thank you. It's -3. Somebody's awake. So we've got -3 and +3, and that adds up to 0. Now, -3 happens to be the oxidation state that nitrogen would choose if it got to choose. Doesn't always work out that way. Let's do a different one with nitrogen. Let's do the nitrite ion. So we think Fa765. No fluorines, no hydrogens, but we have oxygen. What does oxygen choose? -2, because that's the charge it takes as an ion. That's how I remember it. So we've got a total of -4 charge here. Nitrogen has to be whatever is necessary to add up to -1. So this is -4, and so here the nitrogen is +3. Okay, so here the nitrogen was +3, here the nitrogen was -3. Just depends on what else it's with, okay? The CCl4, again, we think Fa765, no fluorine, no hydrogen, no oxygen. Group 7, yep, we got group 7. Chlorine makes a -1 ion, and so it's going to have a -1 charge. Oxidation state when it has a choice. So it gets to pick first because this is the list we made. So we've got 4 chlorines. They are each -1, total of -4. What's the carbon? +4. There's only one of them. +4. Okay? We're not going to get really big into oxidation states, but you need to know what I'm talking about. Okay, so this is the half reaction method, which if you took Chem 1A here at Fresno City College, you should have learned, but I'm not going to assume that. And even if you did learn it, I'm not going to assume that you remember, because, yeah, it's a lot. So this is one of those concepts that involves remembering a series of steps to do. Kind of like finding an empirical formula. There's things you have to do. You can't just like do dimension analysis or something. So the first step, assign oxidation states and identify the substances being oxidized and reduced. I'm going to be honest with you. This is a good thing to do. It is not absolutely necessary. You can skip that and do this just fine, okay? Sometimes you will need to know what's being oxidized or what's being reduced, and so then if you've done that first, that might make things easier, but this one is actually optional. We're going to separate the overall reaction into two half reactions. One will be oxidation, one will be reduction. We can actually separate those and get them correct without realizing which one is which. Then you're going to balance each half reaction. First, with respect to mass. So that's with element, the number of atoms of each kind of element, right? So the first thing you do is you balance everything but hydrogen and oxygen. Then you balance oxygen by adding H2O. And finally, you balance the hydrogen by adding H+. We're balancing aqueous equations in acidic solution. So there is water everywhere. So is it okay to just add H2O as a reactant or a product? Yeah, it is. It's there. Is it okay to add H pluses? Yeah, those are there too. I mean, H pluses are present in neutral water, right? Pure water. But this is an acidic solution. There's extra hydrogen ions. We do the hydrogen ions last because when we balance the oxygen, that's going to introduce an imbalance in hydrogen. And so if we do oxygen last, it's going to mess up the hydrogen. We do hydrogen last, it doesn't mess up anything, okay? So everything else, then oxygen, then hydrogen. Then you balance each half reaction with respect to charge. And we do this by adding electrons. You can add electrons as a reactant or a product. What we're trying to do is make the sum of the charges on each side of the arrow equal. It doesn't need to be zero, it just needs to be the same. Okay, and we're going to do some examples. Then we need to make the number of electrons in both half reactions equal. What we want to happen is when we add these two half reactions together, the electrons cancel out, they disappear. They are being transferred, but it's happening sort of behind the scenes. It doesn't show up in the overall equation. Well, the way we can do this is by multiplying one or both half reactions by a small whole number so that we get the same number of electrons in each. We add the half reactions together. The electrons should cancel out because that's how the process is designed. And there are some other species that might cancel as well. Often those are hydrogen ions or water molecules. And then you should always double check. Make sure that your reaction is balanced with mass and charge. Okay? So this is a very simple example. But if you think about balancing this with just by inspection, you would look at that and you'd say, well, there's one aluminum on each side and one copper on each side. What's the problem? This side has an overall positive 2 charge. That side has an overall positive 3 charge. How did that happen? To be balanced, it has to be the same. So the half reaction method is what we're going to do. Assign oxidation states. Well, let's just do that to practice. What's the oxidation state of aluminum? 0. It's an element. What's the oxidation state of copper ion? 2+, +2. What's the oxidation state of aluminum? 3. And the copper here? 0. With monatomic ions, oxidation state is just the same as the charge. Charges are written with the sign after the number. Oxidation states are written with the sign before the number. I'm not going to try to trick you on that, but if you're wondering why I do it backwards, sometimes that's why. Okay, 2 half reactions. And we just need to use some common sense here. So I'm just going to start with the first thing first. I'm going to draw a line here. I want to keep my arrows lined up. And so I'm going to have aluminum on this side. And then I have to choose which of these products goes on the other side. Well, it should be obvious. It's got to be the aluminum ion, because I can't turn aluminum into copper, right? That's just not ever going to work. So aluminum over here, that's aqueous. Usually when you're given a redox reaction to balance, it has 2 reactants. One will be for the reduction half reaction, one for the oxidation reaction. And then what goes on the other side is whichever of the products looks the most like this one. So the other half reaction is going to be Cu2+, and then that's going to turn into solid copper. Okay? Any questions? Separate into 2 half reactions. Done. Balance the half reactions with respect to mass. Well, 1 aluminum, 1 aluminum. It's already balanced. 1 copper, 1 copper, already balanced. Actually, let's check these off. Now we need to balance with respect to charge. If we look at the first one here, on the left we have 0 charge, and on the right we have +3 charge. We need those to be the same, and we're going to fix it by adding electrons. Electrons have negative charges, right? So I'm going to add the electrons to the positive side. If I add 1 electron, I've got 3 minus 1, now I've got +2. But I need it to be 0. I need 3 electrons. Sometimes it'll be kind of obvious. Other times you may have to write some numbers down and do a little bit of math. How do I balance the second equation? 2 electrons, and on the left side. One half reaction will have electrons on the right, and one will have them on the left. Because here aluminum is being oxidized. So aluminum is losing electrons. The copper is being reduced, +2 to 0, and so the copper 2 ion is gaining electrons. So oxidation and reduction. Okay, balanced with respect to charge. Make the number of electrons equal. If we add these together, the 3 and the 2 are not going to cancel each other out. So we have to ask ourselves, well, what can we multiply this by? Yeah, so we can multiply by 2, and then if we multiply this one by 3, we'll end up with 6 for each, right? So I'm multiplying this by 2. I'm going to go ahead and do that. Maybe I'll do purple for this. So that's going to be 2 aluminums and 2 aluminum ions and 6 electrons. Down here I'm multiplying by 3. This is going to be 6 electrons and 3 copper ions and 3 copper atoms. Okay? Add the half reactions together. So the electrons are always going to cancel out because we set it up that way. So these guys are going to cancel each other out. Copy down everything else. You can cancel stuff as you copy it down, or you can wait until after you've added them and then cancel things. It really doesn't matter. I tend to just keep the same order that they have in the original. It doesn't matter. So 2Al solid plus 3Cu2 plus aqueous is going to make 2Al 3 plus aqueous plus 3Cu solid. Add them together. Any questions? And then verify. So we'll go through and check. We have 2 aluminums, 3 coppers, and then let's look at charge. 3 times 2, positive 6 on that side. 2 times 3, positive 6 on that side. Verified. Any questions? Let's do another one. Make 2 half reactions. What's the reactant in the first half reaction? H plus. Why? Well, because it was first. What's the reactant in the second one? Cr solid. Why? Because it's the only one left, right? So we're going to take our reactants. There's usually going to be 2, and you're going to make a half reaction with each of them. So then for the products, H plus is on this side. We're going to choose the product that is most like it, right? So that's going to be H2. And then down here, Cr2 plus is the closest to Cr. Two half reactions. Check. We skipped that one. Balance with respect to mass. Other elements first, then oxygen, then hydrogen. Okay, well, this doesn't have any other elements. Here, this has other elements. 1 chromium, 1 chromium. Okay, already balanced. Check that one off. There's no oxygen in here, so we don't have to do anything with that one. What about the hydrogen? Well, here we have H2, we have 2 hydrogens, and over there we have 1 hydrogen. So we need that to be 2 hydrogens. Now we balance for charge. In this top reaction, we have plus 2 on one side, so what do we do with the electrons? Add 2 on the other side. No, add 2 on this side. I don't know why my tired brain said put them over here. But then it thankfully quickly realized, well, but then I'd have 2 minus and 2 plus, and that's exactly opposite of what I want to do. I'm going to put it over here. And then down here, what do we need to do? 2 electrons on the other side. So again, make sure that you're adding electrons on the reactant side for one and on the product side for the other. If you aren't, then something has gone wrong. Either you balanced with mass wrong or you're adding up charges wrong, but just stop and fix it right there. So we balance for charge. Make the number of electrons equal. Well, they already are. Cool. Add them together. So the 2 electrons are going to cancel out. We're going to end up with 2H plus aqueous plus Cr solid goes to H2 gas plus Cr2 plus aqueous. And verify 2 hydrogens, 1 chromium, 1 chromium. Total of positive 2, total of positive 2. This one could have been balanced by inspection, but many of them cannot. Any questions? One of the important skills that we need from this type of exercise for the rest of the chapter is being able to write balanced half reactions, because we're going to be looking at half reactions a lot. Okay. I think we've got another example. Now we don't have the little notes over here. Balance the redox reaction in acidic solution. So I'm going to give you a couple of minutes to get started on that and see how far you can get. Okay, that seems like an eternity. It was just a few minutes. How are you guys doing? Making some progress? Okay, let's go over it. What do we do first? Separate into half reactions. So, what's on the left for the first one? Fe2 plus. And, oops. What's on the left for the second one? The MnO4 minus. Okay, then on the right, for the top one, we have the Fe3 plus. I always try to leave a little space here because I often need coefficients. And then down here, it's going to be the Mn2 plus. Next up is what? Balanced mass, right? Well, the first one's fine already, yeah? And the second one, we have a little more work to do. So we balance everything but hydrogen and oxygen first. So 1 manganese, that's all cool. We balance oxygens by adding H2O. If we don't add H2O, how the heck are we going to make oxygens appear on that side? We can't, right? So we need 4 oxygens because we've got 4 on that side. So we're going to add 4 H2Os. And that's not just pulling things out of nowhere. It's an aqueous solution. They are there. Balancing the oxygens introduced a problem because now we have hydrogens as well. So what do we do for that? We're going to add hydrogen ions to the other side. 2 times 4 is 8 hydrogen ions. And if that number seems a little high, it's okay. I mean, sometimes it ends up being like 25 or something. So we sometimes see larger coefficients in these types of reactions. Okay, so we've got mass balance. Now what do we do? Electrons to add to balance the charge. I have +2 and +3. So I'm going to add electrons to the more positive side to make them match. So 1 electron there. Now this one is one where it's a little more complicated to see what the charges are, right? So I've got 2 plus here, and I have -1, and I have 8. So over on this side, I have +7, and over here, I have +2. This is the more positive side, so I'm going to add electrons over there, and how many do I need? 5. Because if I have, whoops, if I have -5 and +7, I'm going to get +2. When we add these together, we need the electrons to cancel out, so we need to get the number of electrons the same for each reaction. This one has 5, that one only has 1. So we'll multiply this top one by 2. No, I don't know where that came from. Multiply it by 5. Good grief, what's wrong with me? This becomes 5, 5, and 5. And then add them together. The electrons cancel out. And we write down what's left. Go back and double check that you've got the same number of each kind of atom and the same number of charges. Any questions? This is something that just requires some practice. Will there be a question like this on the exam? Yes, there will. There will be. Okay, let's see, what do we have left here? Oh, we got time. Okay, so let's do this one. I'll give you some time. Okay, it looks like you guys are making good progress. Let's just go through this one. So I'm going to make 2 half reactions. So CuS going to Cu2 plus AQ, and NO3 minus AQ going to NO2 gas. I'm going to balance for mass. First one's already balanced. The second one, balance everything but hydrogen and oxygen. So here I've got nitrogen and nitrogen, that's fine, but here I have 3 oxygens and 2 oxygens. So I need to add H2O over here, so I get 3 oxygens. That introduces hydrogen, so now I have to add H pluses. 2 H's here will give me 2 H plus over there. If you have a question at any time, please interrupt me. Okay, now balance for charge with adding electrons. This side is more positive, so I'm going to add 2 electrons there. And down here, the right side is neutral, 0. And over here, I've got +2 and -1, so I only need 1 electron. -1, +2, -1 adds up to 0. Make the number of electrons equal. Well, this is 2, and this is 1. We're looking for the least common multiple, if you remember that idea. So I'm going to multiply this by 2. I really like to write this out here, especially when you've got one going by 3 and one going by 2, because otherwise I found I do it wrong a lot. So this becomes a 2, this becomes a 4, 2, 2, and 2. Add them together. Electrons cancel out. Copy down everything else. Bless you. Remember that the order that you write these down in doesn't matter, and even mastering chemistry and my open math understand that, because 2 plus 3 is 5, and 3 plus 2, also 5. Any questions? Okay, so what if we're balancing a redox equation that is happening in basic solution? There's one extra step. The only thing we have to change is that we can't have H plus ions in our final equation. So what we're going to do is we're going to add hydroxides to both sides to neutralize the hydrogens. And when they neutralize hydrogens, they give us water molecules, and then we'll have hydroxide on one side instead of hydrogen ions. You can do this in the middle when you're doing the mass balancing, or you can take care of it at the end. Okay, actually, let's do this. Let's pretend that this was in basic solution. How could we fix it? How could we make it for basic solution? I'll do blue for basic. We've got 4 hydrogen ions. That's the problem. This is all balanced. We don't want to mess anything up, but I'm going to add 4 hydroxide ions right there. And so those are going to turn into 4 H2Os, right? And then I also have to add 4 hydroxides. Well, let's try that again. 4 hydroxides to that side to not mess up the balance. So what I'm going to do, because I need this space down here, is I'm just going to move that up there. And cross this out. This is balanced now in basic solution, but we've got water on both sides. I have 2 water molecules over here, and I have 4 of them over there. So I need to subtract 2 from each side. So I'm going to get rid of those 2, and I'm going to get rid of 2 of those. And then you would copy it out neatly. Make sense? The process is the same. One extra step. Okay, let's do this example. Yeah, well, take some time and do it yourself. Okay, I'm going to go through this guy. We're going to skip the first step of identifying oxidation states and stuff. We're just going to write 2 half reactions. I picked I minus because it was first. And I picked I2 because it's the closest to that. So then here we have MnO4, minus, and the MnO2 will be the product. Balancing with respect to mass, I have 2 iodines and 1 iodine, so I need a 2 here. 1 manganese, 2 oxygens, 4 oxygens. So I balance that by adding 2 water molecules. So I have 4 oxygens, but now I introduced hydrogen. So 2 times 2 is 4 hydrogens, so I need 4 hydrogen ions over there. And then I'm going to balance for charge. This is -2 and this is 0, so I need 2 electrons here. This side is 0, +4 -1, so this is a +3. I need 3 electrons over here. I did the example of making it basic at the end, so here I'm going to make it basic while I'm balancing the half reactions. So I'm looking for hydrogen ions, because in basic solution there's not going to be hydrogen ions. So I'm going to add hydroxide ions to neutralize the hydrogen ions. But I balanced this already, I don't want to mess it up. So I need to do the same thing to both sides. Otherwise it won't be balanced anymore. And I screwed that up because I put a 2 there instead of a 4. Okay, 4 hydroxides and 4 hydroxides. 4 hydroxides and 4 hydrogen ions are going to turn into 4 water molecules. So these guys become 4 H2O liquid. So those neutralized each other. That's a weird looking 4. So, not much better. Oh well, it's not a good day for 4s. I can simplify here, or I could wait till the end. I've got 2 water molecules here and 4 water molecules there. I could subtract 2 of them from each side. So if I take away 2 water molecules, then this 4 becomes a 2. Okay? Now we need to get the number of electrons equal. This is 2 and 3, so I'm going to multiply by 3 up there and by 2 down here, so they're both going to end up with 6 electrons. So the top one I'm multiplying by 2, that becomes 6. I'm multiplying by 3. 2 times 3 is 6, and this is 3, and this is 6. And then down here I'm multiplying by 2, so this becomes 6 electrons. And this becomes 4 waters again, and this is 2 and 2 and 8. Again, if you have questions in the middle here, please interrupt me. So adding them together, the electrons cancel out. And copy down what's left. 6I minus plus 2 MnO4 minus plus 4 H2O liquid. There will be times where you might have H2Os up here as well, and so you may have to cancel H2Os as you're adding these together. In this example, we don't have that happening. And 3I2 plus 2 MnO4, nope, MnO2 plus 8 hydroxides. Any questions? Okay, so here's one more example. Go to it. Okay, so again, You've been working on this on your own, so I'm going to go through it kind of quickly. Stop me if you have any questions. So we make two half reactions. So ClO minus, oops, fix that. And the Cl minus is going to go on this side. And then the CrOH4 on that side. A little squishy, but that's okay. And CrO4, 2 minus, over here. Now we balance for mass, everything but hydrogen and oxygen. 1 chlorine, that's all good. 1 chromium, check. Now we balance oxygens with water. This is 1 oxygen and no oxygens. So you can do the hydroxide part at several different points. I'm just going to do it now. So I've got 2 hydrogen ions here. This is basic solution, so we can't have that. So I'm going to add 2 hydroxide ions, or 2 moles of hydroxide, to get rid of that, to neutralize it. And then I have to do the same thing to both sides to keep it balanced. So together this becomes 2H2O. I'm going to write it over here because I happen to have space. 2 of them. Down here I have 4 hydrogen ions on this side, so I'm going to add 4 hydroxide ions to each side. And the hydroxides and the hydrogen ions become 4H2O. Pretty good so far? Okay, balance for charge. We might be tempted to start canceling things. Don't do that yet. Balance for charge. Make electrons green this time. So over here I've got 0 and -1, and over here I have -1, and that kind of looks like 20 H minuses, but that doesn't make any sense. 2 OH minuses, so -2, and another is -3 on that side. So I need 2 electrons over here. In the bottom, I have 4 plus 1, I have -5 over here, and -2. So I need 3 electrons in there. Things are getting messy. Make the number of electrons the same. I have 2 and 3, so I'm going to multiply the top one by 3 and the bottom one by 2. So I'm going to go through and do that. So 2 becomes 6, 2 becomes 6, this is 3, 3, 3, and 6. Bottom multiplying by 2, 4 becomes 8. I'm going to squeeze a 2 in there, and a 2 here, and this becomes 8, and that becomes 6.